Okay, I think you can start. So, good afternoon, good evening, everyone. This is NOC 25WD110 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudeb Dasgupta. I'm Debashish from IIT Kanpur. I'm one of the TAs. So, as you know, that we go live every week from 7 to 9 on each Saturdays. So today we are at week 9. So a brief announcement that next week I will not be able to take the session on next Saturday. So it is preponed to this Monday, means day after tomorrow, 6 to 8 p.m. Okay. So if you are interested, you can join if you are available. So that is this Monday, day after tomorrow. Okay. So what we plan for this week is to, by the way, am I audible? Can anyone confirm? Okay, fine. So yeah, so what we plan to do today is basically some basics of the analog circuits. Okay, so we'll try to build up some concepts while solving the numerical problems. So the first question is, a sinusoidal signal with a period of 1 second has a peak of 2.5 volt. So if you draw the sinusoidal signal, basically, let's say the signal is x of t with t. So it has a peak of 2.5 volt, 2.5 volt, and a negative peak of minus 2.5 volt. So at 0.25 seconds, let's say this is 0.25 seconds, it has a peak. Then at 0.75, sorry, let's take this point, 0.75 second. At this point, it has a throw or dip, and then so on. So the sinusoidal signal will somewhat look like this. Okay, then this is weird. Let's say around 1 second, and it will just move on with the period of 1 second. So this is the time period of 1 second, right? So the question is, this signal is applied to the input of a common drain amplifier. Find out the value, output value at the time instant equal to 2 seconds. So basically, they are saying, let's say this is common drain amplifier. You have this xt. You need to find out yt at t equal to 2 seconds. So any idea how do you proceed for this? So basically, let's say this is your MOSFET. So it has 4 terminals. So this is drain, gate, source, and then this is body, right? So what do I mean by common drain? Common drain means first you need to understand what a two-port network is. So I will convert this into a two-port network. Basically, a two-port network will have this kind of, it will have generally 4 terminals. This will be your input port, this will be your output port. Fine. So another way a two-port terminal can be drawn with 3 terminal is like this. This become your input port, this become your output port, and this terminal we called it as a common terminal. Okay. So basically input is applied between one terminal and the common terminal, and output is also taken from a third terminal, and that is referred to or referenced to the common terminal. Fine. So this terminal can be anything. In our case, it is mentioned as this is drain. So this will be your gate and this will be your source, because mostly your you generally apply for amplification or transistor action, you generally apply your input to the gate terminal. Fine. While your drain is common. So this will be your input, and let's say B terminal is shorted for NMOS and PMOS. Mostly this is shorted to each other, right? So I can as if remove this one for the time being. So this is your S. So your output will be taken from this. This is your output. Fine. And this D terminal is your reference terminal. So understand one thing very carefully, that let's say now this is my MOSFET. So this is D, this is G, this is S. For the time being, I am assuming that the body and source are connected to each other. So I'm not showing explicitly the body terminal. Okay. So what do I want to amplify? So I want this, right? Basically, we want to amplify a small signal around a bias point. This we have discussed earlier as well. What small signal means and what is bias point, what small signal means at the initial lectures. Okay. So in small signal sense, your voltage sources are, so I'll be more specific, your independent voltage source is replaced by, in small signal analysis, what is your independent voltage source becomes? DC voltage source.
Connected to ground.
No, that is not the right word, right? DC voltage source is
Nullified.
null. That means voltage source becomes zero or short circuited. So why it is connected to ground? Because let's say this is your voltage source, right? This is node A and this is, let's say it is connected to some node B. When you will do small signal analysis, what you do, you just short it. And it happens to be that at the drain and other terminals where you apply your biases, this terminal is grounded. That's why you mention that it is connected to ground, but it is not the correct term. The other potential may not be fixated at ground or zero voltage. Fine. So voltage source is null. or voltage source is shorted. Similarly, what about the current source? Similarly, your
Open circuited.
independent DC current source is open circuited. Okay. So if that is the case, for this analysis, we can assume that my drain is grounded because drain is my reference terminal or common terminal, and your input is applied to this terminal. Let's say this is your V in, and output is taken out as this terminal. So let's say this is your V out. Okay. So now you have the situation something like this. This is grounded. This is your V out. This is V in. So can you tell me, uh, can it sustain some voltage V out if I do not connect anything at this terminal? The question is, I need to connect one resistance here. Let's call it source resistance. Without this resistance, can my V out sustain? Or let's say, if not a resistance, I need to connect some sort of current source to bias this. But then again, it is not a small signal picture. So what is your current source? So your actual circuit will look like the full circuit of common drain stage will look something like this. You will have a fixed current source biasing. Then you will apply here your DC voltage plus your small signal input. This will be basically biased to your VD, and then you take your V out from this node. Right? Now it happens to be that your current sources are not generally ideal. So it will always see a resistance parallel to this. Let's say this is the resistance of the current source. Now when you draw the small signal equivalent, this circuit simply becomes this. This is your V out, this is your V in, and this is grounded. Is that okay?
Yes, sir.
So this is your common drain stage or common drain amplifier. Okay. Now, how do you solve this small? How do you calculate the gain of this amplifier? What do you generally use? Can you tell me? I'll provide you some better tool to analyze this easily. Some better representation. Okay. So can you tell me how do you analyze it at this moment?
By applying KCL at the output side.
No, by applying KCL at the output side, but you draw first the small signal equivalent circuit, right?
Yes, sir. That we have to do.
So basically what you currently do is, so you currently draw it like this. So you connect your G, then you connect your, let's say this is my S terminal, and you will have your this RS connected. This is your V out, and then you have your input connected between this get to drain, and from drain to source you connect this current source. And what is the value of this current source will be?
GMVGS.
Gm times what is your VGS here?
V in minus V out.
So V in minus V out. And then you apply your KCL at this node and solve it, right? So why do you consider this as an current source? First thing, this is a voltage controlled current source, right?
Yes, sir. Because in for MOSFETs, we generally for amplifier application we bias it in saturation region, and in saturation it behaves like a voltage controlled current source.
So from this plot, can you tell me if it is a voltage controlled current source or not?
Yeah, if we bias it in the constant current region, we can say.
Okay, let me just demarcate this for you. So this is some random dashed line. So let's say you are biasing it in this regions. Okay. So why is it a current source?
Because it does not depend on the ID value does not depend on the VDS. Even if we change VDS, the ID remains constant.
So your constant current source is basically, let's say if I have a current source of I0, so it gives me a value like this, right? Let's say the current is flowing ID and the voltage across it is VD, and this will be your I0, right? So whenever you see on your IDVD characteristics this kind of straight line, you can easily state that it is a current source. Now, why is it a voltage control current source? Because the value you can change with respect to VG. You can hop from one point to, let's say you are here now, then if you increase VG, you are at different value, then increase VG, you are at different value, right? So it becomes a voltage controlled current source. So that is why we do it like this. But what I'll tell you that from now on, to analyze this kind of circuits, no, you don't need to draw this. No need to draw it in terms of your current sources and this voltages, resistances, etc. Right? If you understand it, what the concepts behind it, you can directly analyze your circuits in this itself. Fine. So how will we do small signal analysis from now on? So small signal analysis, we'll just draw the circuit in a small signal sense. So that means current sources becomes open and voltage sources become short. So this becomes this. Okay. So this is my small signal equivalent of the circuit. Now what I understand is that these are the two nodes. These are the two nodes, and whatever value or the voltage difference between these two nodes we have, Gm times that current will be flowing through this transistor. Fine. In the direction for NMOS from D to S or drain to source. So I can simply write this current to be Gm times, and this voltage, you know, it is V out. So I can simply write this current to be Gm times V in minus V out. Okay. And what about, okay, just I'll come to that sometime. So this, if you draw this much, then can you tell me what is your V out? by looking at this circuit. What is my V out? So this is the current flowing through the transistor, right? It has to flow through this R to the ground because there is no other path.
Yes.
So this V out will have to be this current
Times RS.
times RS. Now you can easily simplify V out by V in as Gm times Rs divided by 1 plus Gm times Rs. So what I am asking you to do, to skip this step, okay? It will save you a lot of time. If you can understand it directly from this circuit, so it will save you in your exams drawing the small signal equivalence, okay? We'll see, there are other tricks and other circuits. I will come to that, how we do about for those circuits, and what if I have output conductance as well, right? So in this case, what do you think the relative value of GM and RS can be? GMRS is basically your gain of a stage, right? Some transconductance times some resistance. The unit of GMRS will be a unitless quantity. There is no unit of GMRS. So generally, your GMRS will be much greater than 1. So can I write my V out by V in equal to 1?
Yes.
So this is so what we have seen, common drain amplifiers generally provide a gain of 1. So what is the significance? When do I need a gain of 1?
We can use it as a buffer, voltage buffer.
It is used as a voltage buffer. And I think I have discussed why voltage buffers are used to avoid loading effects in circuits, right?
Yes.
So we'll
And
see that,
impedance match.
yeah, and impedance matching as well. So these voltage buffers will use extensively in the next lecture. So that is why I wanted to emphasize on this point, that this I will use in designing the fully differential amplifier, okay? Because I need to show you that how that fully differential amplifier structure came about, okay? So there we will be using this voltage buffer. So remember that voltage buffer stage, wherever required, we can use it directly by the common drain amplifier stage. Fine. So now if you have a sinusoidal signal, so your yt will also be, yt will have a gain of what? Yt will have a gain of approximately 1. So yt will also follow the same input signal, right? So the question is, find out the output voltage at the time instant equal to 2 seconds. So where at the nodes of the signal, you can see that at 0.5, at 1, then at 1.5, these are the nodes of the signal where you get a zero value. So obviously at 2 seconds, you will not get any output signal, right? Assuming that there is no phase shift between the input and the output. That means we are well beyond the, well below the cutoff frequency of the signal. We'll discuss about those things. So there is no phase shift between the, no phase shift between input and output. What is the gain of a common source amplifier in terms of GM and Rout?
minus GMRD.
So if it is minus GM-RD or minus GM-Rout, so what will be your phase shift there?
180 degree.
180 degree, right? So remember that. So we'll have 0 at 2 seconds. And this is because my common drain stage will give the exact value of the input at my output side. Now for these circuits, for example, I do not have a ideal current source, right? Let's say I have some kind of CLM or channel length modulation. So I will have this kind of structure. Then how do you draw this? You connect a resistance parallel to this. This you call it as R out, right? The same thing you can do in this circuit as well. Just connect a R out parallel to your this current source or GM times V in V out, V in minus V out. Okay. So remember that. Okay. So let's move on. Calculate the small signal gain of the given circuit if this. So yeah, this is a, what is this circuit? What kind of amplifier or what kind of stage is this?
Common source.
And how can you say that?
So the input is connected between the input and output, both is taken across the source terminal.
So this is your port 1, this is your port 2, right? So this is your common port. So this is your input and this is your output. So, okay. So if we start analyzing the circuit, we need to find out the gain, right? So small signal equivalent, again we'll skip the small signal detailed circuit part and we'll just, so this is my, this will be grounded in small signal, this is RD and this is my V in. So what current is flowing in this? GM times V in, right? This entire, and what is the output? Output I am tapping out at this point. So from this circuit, this GM times V in has to flow at this also. So it is flowing from ground towards V out, right? So V out I can directly write the current times the resistance. Okay. So my V out by V in or the small signal gain becomes GM times RD. And it is mentioned that lambda is equal to 0. That means this parallel resistance or RDS or Rout is equal to infinity. Okay. So I can assume it as an open circuit. So this means your RDS or Rout equal to infinity. Fine. So now RD I know. RD is given as 1 kilo ohm. We need to find out GM, right? So how do we find out GM? So first tell me,
So your voice is breaking up, I guess.
is it so? Is it okay now? Just let me check internet connection. Is it okay now?
Yes, sir, better.
Okay. So finding out GM. So can you tell me, is GM a bias dependent quantity?
Yes, sir, it is.
Why?
Because from the formula we know that GM is 2IT
No.
by.
Tell me physically. Formula maths, we know that it will be dependent on that, but try to interpret that plot, that formula into some in the plot, in the plotting sense, or in some kind of IDVD input characteristics, and then answer.
So, sir, in the IDVDS, IDVG characteristics, if
Hmm.
we plot it, so we get a non-linear curve basically. So at different
Exactly.
sequence of that, we get different GM.
Exactly. So due to the nonlinearity, I get different GMs, right? For example, if my bias point is this, let's say this is VGS1, and I take another bias point, this is VGS2. So what kind of slopes I will get? The slope is like this, and at this point the slope is like this. So obviously your GM2, this is GM1, and GM2 will be completely different. So for any nonlinear curve, my GM is basically del of ID by del of VGS at Q point. So even to find out small signal gains, I need to do the DC analysis of my circuit first, fine, to find out the small signal parameters. So this is a small signal parameter dependent on DC bias. And do you know why it is? Okay, just let me tell you briefly. So basically, what is happening? Your ID is a nonlinear function of VGS, right? I have modeled it in terms of a square law, right? But I'm not sure. It is in some region it is square law, in some region it is linear as well. So we are not sure. So how do you do nonlinear analysis basically? So if this is, so let's say ID plus small id will be a function of some DC voltage plus some small AC voltage. Okay. So any kind of nonlinear characteristics I can expand in Taylor series. So I can expand it into Taylor's series. So what I'll do, first term will be VGS, second term is this dash of VGS times small VGS, that is the small deviation, or VGS plus small VGS minus capital VGS will give me the same thing, small VGS, plus F double dash of computed at the point VGS or the DC bias times VGS square by factorial 2 plus higher order terms, right? Now you say that your VGS is a small signal. You say that this is small. Then what you do? You can ignore these terms. For example, if VGS is, let's say, 0.1, what will be your VGS square? 0.01. So you can easily ignore that. But what if your VGS is 0.9? So your VGS square will be 0.81, right? You cannot ignore in this case easily. So your understand this very carefully, that your VGS has to be very small to have this approximation valid, right? So now if you see, your ID plus small id will be f of VGS plus f dash of VGS times small VGS. Higher terms we are ignoring. So this is my ID. So this I can cancel. So what is your small id? Small id becomes f dash of VGS times small VGS. So what is f dash of VGS? did by dVG. So this is nothing but did by dVGS computed at VGS or bias point times small VGS. This is nothing but your GM times small VGS. Okay. So under small signal approximation only, your this every small circuit designs, whatever you are doing, are valid. So the takeaway point is GM is dependent on bias, and that you have to calculate from the DC analysis. So from this circuit, what is given? ID, let me just copy this. So this is 0.5 volt. Okay. So what is your ID in saturation? Half mu n Cox W by L VGS minus VTH whole square. 1 plus lambda VDS I am considering at 1 because my lambda is 0. What is your GM? Mu n Cox W by L VGS minus VTH. What you know? You know ID, you know mu n Cox, you know VTH. VGS you do not know, right? You are not given the bias voltage. So I need to eliminate VGS from these two plots, from these two equations. So how will I do that? If I do GM by root over ID, what will I get? Mu n Cox W by L VGS minus VTH, and in this case I get half mu n Cox W by L times VGS minus VTH. So this will get cancelled. So my GM will turn out to be, so this will be 2 mu n Cox W by L times ID. So this I know, this I know, ID I know. This is 10 by 180 nanometer, 0.18. So 2 times mu n Cox is your 100 micro, W by L is 0.18, ID is 2 milli. Fine, 10 to the power minus 3. So this will come out to be around 4.71 milli Siemens. So what will be your gain? You have found out it is minus GM times RD. RD is 1K. So it will give you minus 4.71. Any question on this? Okay, if not, so let's proceed. Okay, so can you tell me what is this circuit called? We need to find out RD. What is this topology called? First of all, it is a common source. And any specific name for this?
Drain feedback.
Yeah, that you can say. There is a more specific name to this is something called diode connected.
Yes, sir.
So why this is advantageous? Let us ignore the RG for the time being. For example, you are connecting your device something like this. Okay. So why is it helpful?
My MOSFET is always in saturation because the
Yes.
gate and drain is at same potential.
Yes. Your VGS is always equal to VDS, and for NMOS, we know VTH is greater than 0. So your VDS SAT is equal to VGS minus VTH is always less than VGS or VDS. So in other words, your VDS is always greater than VDS SAT. So this ensures that my MOSFET is biased always in saturation. MOSFET is biased always in SAT. Okay. So now coming back to the analysis of this circuit. Okay. So we need to find out the current 1 milliampere. Okay. GM1 we know. So this is VDD equal to 1.8 volt. RD, this is RG, this is M1. So first thing is that if I want to know RD, so ID is also given. So let me highlight. ID is also given as 1 milliampere. So I know my ID. So what do we need to find out to get my RD? I need to find out the node potential at this point or my VD. Fine.
Yes, sir.
And how do I find out my VD? So can you see that my VD and VG are the same potential?
Yes, sir.
Is it obvious to you? Basically, there is no current flowing through the gate, right? So whatever I connect where, how many large resistance I can connect there, if it is not infinite resistance, my VG will be exactly at the same potential as if my RD, as my VD. Okay. So if that is obvious, then I have my GM1. GM1 formula we have noted that it is Cox W by L VGS minus VTH, and also I know my ID. ID is half mu n Cox W by L VGS minus VTH whole square. So if I can find out my VG, I will know my VD. So in this case, what I'll do? I'll do GM1 by ID. Again, I'll have the same thing, 2 over VGS minus VTH. So I know my GM, I know ID, I know VTH, so I can found my VGS. So VGS will be equal to what? GM is 20 milli, this is 1 milli, so this will give me 10, this will give me 20, and this will give me 0.1, and VGS minus VTH is 0.4, right? So VGS will be 0.5 volt. If VGS is 0.5 volt and Vs equal to 0 because it is grounded, so my Vg equal to Vd will be 0.5 volt. So at this node, I am seeing 0.5 volt. So I can easily calculate my RD to be VDD minus VD upon ID. That will give me 1.3 kilo ohms. Is the analysis clear?
Yes, sir.
Okay. So let's move on. The MOSFET gate to source capacitance in saturation region can be given as, any idea? What is the answer? I know that you know the answer, but tell me why it is so if you know the answer. So there is a implicit assumption in the question that we are talking about strong inversion, okay, or inversion above threshold. Why do I say so? By the way, what is your CGS? How is it defined? Okay, this is what is meant by CGS. And in MOSFET, so just let me replicate this. So let's say this is gate, body, source, drain, source, drain, gate, body. So we'll consider two cases. One, we'll consider linear region. Another we'll consider linear region. Let's say for the uh, easier analysis or understanding, VDS will be 0 volt, and let's say in this case VDS equal to VDD. Okay, so how will my charges look like? And let's say my inversion charges are present. So let's say this is at VDD, this is grounded, this all are grounded. In this case, this is grounded, this is grounded, this is at VDD, and this is at VDD. The purpose of this VDD is to mention this is greater than VTH, this is greater than VTH. Okay. So how will my charges look like? Let's say this will be my inversion charges. Okay. But in case of saturation, what will happen? First thing is that my this boundary will expand, and these charges will not be in a rectangular fashion, it will be in a triangular fashion. Now tell me why it will be so.
Because my drain side is at lower potential than my source side in terms of VGS, VG as the
No, this is
capacitor voltage.
this is the drop across this. What you are trying to say is a drop
Yes,
across the oxide.
yes, sir, yes.
Okay. And why do this increase? This side gets
Because
more
it's a
depletion charges.
reverse bias. The
Reverse
drain.
bias PN junction, so the depletion width will increase, right?
Yes, yes, sir.
Okay. So if I tell you to distribute, so uh, this is QB, this is QI, or inversion charge. Okay. So if I tell you to distribute QI between source and drain terminals. Okay. Let's say source, drain, QI. In terms of percentage, can you tell me how much percent will you distribute in this case? In case of, let's say, linear case?
For linear, it would be 50-50 because the charge profile is rectangular, so we can equally distribute.
And what about QI? What about saturation?
So charge, I guess, more will be on the source side and then the drain side.
So there are models which consider 100% at the source side, 0% at the drain side. Okay. But a more accurate picture is 60% on the source side and 40% associated at the drain side, because your surface potential midpoint or the channel midpoint, what we call it as this location, right? Even if you consider that this much charges you want to assign to source and this much charges you assign to drain, then also 100 and 0 does not depict the correct picture. Although you can see that near the drain end, almost in the pinch off region, you will not have any inversion charges, right? So this is what is mostly used in digital designs, or I would say compact models developed for digital design. Okay. However, more accurate way of representation is a linear profile. Okay. Basically, from source to drain, the charge concentration reduces linearly. This particular thing is called Ward-Dutton charge partitioning. Mostly used in compact models of analog designs. So this has more stringent criteria, the models what you will develop, than the digital models, because digital models we do not need to understand what is going in between. We need to understand, but a trade-off is more than sufficient. We need to just capture the on and off state, right? But in case of analog designs, you need to be able to see derivatives and predict charges, capacitance at each and every point in the bias spectrum or bias regime. Fine. So if this is so, and if I draw the charge profile, let's say QG equal to Q semiconductor, whatever the charge in the semiconductor is, or equal to QB plus QI, it will with respect to VG, and let's say this point is my flat band point, and not zero. Flat band may not be zero, so it will be something like this. Okay, so this is your charge profile, and then your capacitance Cg, you get the derivative of this. So this will give you a constant line, then this region will give you something like this, and around this point you will get another constant line. Do you see why it is positive, the capacitance always? Because in this case your voltage is negative, the denominator is negative, and in this case the numerator is negative. So that is why your negative slope is getting converted to a positive value. Okay, and this value is basically your Cox dash times WL. This we have seen. Okay, now where are you at your inversion? Now where are you at your strong inversion, or and also in saturation? Somewhere here, because this voltage will be close to your threshold voltage VTH. This region is called accumulation. This region is called depletion, and beyond this is called inversion. Now I need to find out Cg is equal to dQg by dVg. Fine. dQ B plus QI divided by dVg, dQB by dVg plus dQi by dVg. Fine. Now this dQi I am distributing between source and drain. So these have two components, dQs by dVg, another one is dQ d by dVg. What is the value of this? In strong inversion, we have seen it is Cox WL. Now, what is the charge contribution of QI? %60 and 40%. So, in saturation, my CGS or CSG will be 60% of Cox dash times WL or 2 by 3 of WL.
Yes.
Okay.
But I have sir one question.
Yeah.
Cox is we generally represent is the capacitance per unit area, right? So if we are multiplying with WL, so why we are still using the Cox dash nomenclature?
Cox dash in my notation it is epsilon ox by Tox.
But it is in per unit area, right? I guess.
Per unit area. So overall capacitance you have to multiply with area.
Yes.
So this you will multiply with area, right? To get the overall capacitance. Assume that this is Cox. Okay.
Okay, sir.
Okay. So let's move on. So okay. So find the bandwidth of the given amplifier in the given circuit. The device parameters are this: CGS, CGD. So they have given CGS. This is my CGS. They have given CGD and RD, R signal are given. Values are given, right? So we need to find out the bandwidth of the circuit. So how to proceed? Any idea? Whether what do we need mean by bandwidth? How do we check bandwidth? From what plot?
Bode plots.
So, okay. let's start with a simple circuit. So let's say this is my V in, this is V out, this is C, this is R. So what is the transfer function?
One by SCR plus one.
So this will be 1 by SC divided by R plus 1 by SC. So it is 1 by 1 plus SCR. Fine. So my V out of S by V in of S is equal to 1 by 1 plus SCR. So how do we plot Bode plot from this? So let's call it H of S, or the general terminology of transfer function. So what is S? Sigma plus j omega. This is the loss factor. So if we consider sigma equal to 0, so we go from Laplace to Fourier domain, right? So my H of j omega becomes 1 by 1 plus j omega CR. So now tell me, how do I plot Bode plot from this?
Omega versus AV again.
No. So this is a complex number, right? Either do it in real and imaginary, distributed, or magnitude and phase. That is a polar representation, right? So if I do mod of h of j omega, what will I have? 1 by square root, right?
Yes, sir.
And what about this? What about this? Minus tan inverse omega CR, right?
Yes.
Now, if I plot mod of j omega with respect to omega, how will it look like? This I need to plot it in dB scale. This I need to plot it in log scale. So what is the value at omega equal to 0?
One by root over one plus c square r square.
Omega equal to 0, it is simply 0, right? Or simply 1, right?
Yes, sir. Yes.
And then what is at omega equal to 1 by CR? Let's call it omega 0.
One by root two.
So mod of h of j omega is equal to 1 by root 2. And what is that in dB? 20 log of this, right? Minus 10 log of 2. What is this? Minus 3 dB. Okay. So the point at which it falls to minus 3 dB from its DC value is called basically called what? Three dB frequency or
Cutoff frequency.
cutoff frequency. Why it is called cutoff frequency? See, minus 3 dB means what? Your power is getting halved, right? So this is your amplitude. So power will be a square of this. So if this is 1 by root 2, that means your power is 1 by 2, right? So whatever you
Yes.
are desiring, your output is getting half of that value. So that means that you cannot consider as a desired output. So that is mean as equivalently as it is cut off. For example, in your household supply, if the voltage is getting tripped below 110 volt, so will you call it that your supply is stable? Will you consider to pay your bills if your equipments are getting power supply at 110 below 110 volt? It is not, right? Most of the equipments, electrical equipments in your household will be designed to withstand a certain range of voltage fluctuations. Fine. So mostly it may seem that in dB scale it is just 3 dB, but it is half of the power is gone at this point. So if you want to use this as an low pass filter, this is basically a low pass filter, right? So you cannot use it for these frequencies. Only till this frequency you are allowed to, or you should consider to use that low pass filter. Okay. So this frequency is also called pole of the system. Okay. And this basically, this equal to 0 is your characteristics equation. And the roots of this are poles. Here the poles are negative, that means you have a stable system. These are all coming from your control system concepts. Okay. So then what will you call your bandwidth to be? Bandwidth means the width of frequency or the range of frequency in which you get your desired performance. Okay. So this thing is called your 3 dB bandwidth, or in general bandwidth of the system. There is another terminology that for amplifiers we use at this point where it is crossing the, this is 0 dB, means in absolute scale it is 1. This is called UGB, or unity gain bandwidth. Is it clear till this much?
Yes, sir.
Similarly, what about phase plot? How will it look like? This is simple tan inverse of omega, right? So this will be simply like this. At this point, what is the value at omega 0? What is the value? H of j omega is minus tan inverse omega CR. So at omega equal to 0, it is what? Phase is omega equal to 0. What is tan inverse 0?
0.
And what is omega equal to omega 0 or 1 by RC? Tan inverse 1 is what?
1. So
Tan
it will
inverse
45
1
degrees.
is minus 45 degree, right?
Yes.
45 degree, and then there is a minus. Similarly, what if tan inverse omega is infinity? What is omega?
90. Minus 90.
So this is your phase plot. Okay. So you have to be, whenever you are studying small signal analysis of the circuit or high frequency analysis, you have to be very comfortable with the Bode plots, both the magnitude plots and both the phase plots. These phase plots will give you something called gain margins. Okay, important in amplifier designs. Okay, and also from this you can analyze the stability of your system as well. Okay, for stability we generally see phase margin of the system. So that is not the purpose of today's discussion. So we have understood what bandwidth means, right? So now we'll analyze this. Okay, fine. So so far I have told you that let's say this is a MOSFET. Let's say this is, okay, this is your GM times V in. Let's say this is V in. So another representation that I am going to use is this. Is it okay? This block is called OTA, Open Transconductance Amplifier. Okay. What is conductance? Current at the output and voltage at the input. What is transconductance? I am fetching the current at the output node while I am putting the voltage in the input node. Is that clear?
Yes, sir.
So this circuit will be something like this. So for the MOSFET, I'll have this, and then I think I have RDS as well, right? RD, RD, this GM, I have RDS, I have. So this will be my RDS. So this is my, this MOSFET. And beyond this, I'll start to connect the other stuffs. Similarly, in this MOSFET only, I have CGD. So this is my gate terminal. So I will have this CGD. I have CGS. CGS will be connected at this terminal because my source is grounded. And then I have my RD. RD I am connecting at the output. This is my V out. And then I have R signal. And here I am applying my V input. So my circuit is something looking like this. RDS, RD, V out, CGS, CGD, and then R signal. Okay. So now can you tell me what should be the low frequency equivalent? Low frequency or DC equivalent? So what will I do with the capacitances?
Open circuit.
See, if I open the capacitances, So this is R sig, this is V in. By the way, in this I should mention no current is going into this. Okay, remember this point, because this is your gate terminal. So this is then at output you have RDS. Let us do it in GDS terms. GDS, let us write it as GD. GD is nothing but conductance associated with that 1 by RD. It is just a representation. So let's say this is G signal. So can you tell me what is the gain of this stage? What is V out by V in? So in this case, this V in is appearing at this point because no current is going inside, right? So this current is Gm minus Gm times V in, and that is flowing out of this resistance combination, right? So it will be what? Gm divided by GDS plus GD, or in your conventional terminology, this is nothing but RDS parallel RD. Is that clear?
Yes, sir.
So that is your DC gain, okay? AVDC. Now I want to represent this same circuit in this form. CGS, CGD1, let me just club it for the time being. This becomes my GDS plus GD, because this will be in parallel always. So basically what I am doing, I am decoupling this into two capacitances. How can I do that?
Miller's theorem.
So what does Miller's theorem tell you? So Miller's theorem tells you Miller's. So let's say we have a stage K. This is your input node. This is your output node. If you have some impedance Z connected to it, it can be distributed as Z1, Z2, and it remains 1 and 2. So what is the value of Z1? Z by 1 minus K. Z2 is 1 by Z by 1 minus 1 by K. Do you know the proof of this? It is very simple. Just connect a V test at this point and check the current. Okay, as you know current is flowing through this, then you will easily get these values. Okay, so I'm not showing you the proof. That are easily available in online. They easily available online. So I'll just tell you one catch. Let's K is a gain stage. Okay, that means let's say K equal to 5, and let's say Z equals to a simple resistance. Let's say 5 ohm. So what will be Z1?
minus 5 by 4.
Or let's say 4 ohm. So Z will be how much?
Minus 1.
And what about Z2? So 1 divided by 5, 1
1 by 5.
1 minus answer, 0.8, that is 1, and that is 4
Minus 1 by
divided
5.
by, so 5 ohm, right? Z is 4, right? K is what? K is 5, 1 by 5 is 0.2, 1 minus 0.2 is 0.8. So 4 by 0.8 is equal to 4 into 1.25 will be 5, right? So do you see something weird about this?
Negative impedance.
Negative resistance. So should we be worried about this? Basically, whenever you will do some amplifier design, no, at very high frequency, you will often encounter with this kind of negative resistances. So you always understand that that is coming due to there must be some feedback between the gate and drain, which is when you calculate the input impedance, that is being looked when the impedance is being looked at the input side, that is getting Miller converted, and you are seeing a negative resistance, right? This creates stability issues and can be solved by matching networks, okay, or impedance matching networks. So this is just a heads up. In any time if you see some negative impedance, don't just get worried. You have to think that it may come from the Miller effect if the stage is a gain stage. Fine. So you have to have a gain stage, means your input and output has to be amplified somehow. Okay, if that is done, then can I directly write my CGD1? So what is this? CGD is equal to impedance associated with it is 1 by SCGD, right? So your Z is 1 by SCGD. So what will be your Z1? Z1 will be 1 by SCGD divided by 1 minus gain. What is your gain? Gain is minus GM RDS parallel RD right? And this Z1 is nothing but 1 over SCGD1. Fine. So from this we can write CGD1 is equal to CGD1 is equal to what? SS will get cancelled. It will be CGD times 1 plus GM RDS parallel RD. Okay. Similarly, you can find out CGD2. Similarly, find out CGD2. Fine. Now you have all the tools to calculate the bandwidth. So now what will you do? You have V in here, let's say R signal here, and let's make it RDS parallel RD for the convenience. So you have, let's say, Vx. So you need to compute what? You need to compute V out by V in, that is your V out by Vx times Vx by V in. What will be your V out by Vx? V out by Vx. We have seen, right? When calculating DC, I will have what? V out by V in will be simply minus GM times RDS parallel RD parallel 1 over SCGD2 times, this is my V out by Vx, and let's say my Vx by V in will be what? 1 over CGS plus CGD1 divided by CGS plus CGD1 plus R signal. Is that okay?
Yes, sir.
This is a series combination. So now you have H of S. Next step, what you do? You simplify H of S in the form okay. And why it is easier to do? Because you already have one pole associated with this and another pole associated with this. So these numerical calculations you can do, right? But I'll just tell you the crux. What is happening? So let's say this is your omega and this is your H of S. So from this equation, let's say this is equation A. From equation A, can you tell me what is the value at S equal to 0?
H0.
and this will be equal to the DC gain of the system. You can cross check that. It will be minus GM RDS parallel.
Yes, sir.
And let's say at this point you hit a pole, omega equals to P1, let's say. So what will be the slope after that? So this I think I have not discussed. So this slope, this slope is minus 20 dB per decade. Why it is so? Because let's say if your h of j omega is 1 by 1 plus j omega r, okay? And let's say you take 20 log of this. So this will be what? Minus log of 1 will be 0, minus 20 log of 1 plus j omega r. So if you plot, this will give you what? H of j omega in dB. So if you plot h of j omega in dB versus log of omega, so you will get a slope of minus 20.
Yes, sir.
So that is why it is minus 20 dB per decade. So now let's say you have a frequency. So it will have a minus 20 dB per decade slope, and then after some time it will hit another pole, this P2. And what will be the slope after that? It will have minus 40 dB per decade slope. And why I am telling this? So what I have assumed that P2 is greater than P1, right? So now let's assume a frequency omega that is less than P1. So obviously it will be much less than P2. So in this case, I can ignore these terms, both terms, right? In this case. So that means my h of s will be a constant value. So this is giving me the region at this point, at this region. Similarly, let's say I am taking P1 less than omega less than P2. Then my h of s will be can be approximated as 1 plus s by P1. Fine. And then this s by P1 I can simply consider s by P1 because that will be more than 1, because s is nothing but j omega, right? So omega by P1 will be more than 1, but omega by P2 will be less than 1. So I can take this quantity, second quantity, to be 1, this quantity, ignoring the pole. So I will have h of 0 divided by, let's say, P1 divided by s. So this s is giving me minus 20 dB per decade slope. So this condition is giving me the region here. And what about the third case? Let's say omega is greater than P2, right? So obviously S by P1 will be much greater than 1 and S by P2 will be much greater than 1. So my H of S will assume a form of H of 0 divided by S by P1 times S by P2. So two S are getting multiplied. That means 2 omega square. I am having omega square. So this square when log scale, that minus 20 dB minus 20 log omega square will give me minus 40 of log omega. Okay. So this will give me minus 40 dB per decade of slope. So now if I highlight it in blue, so this will be this region. But from the amplifier point of view, what should be your bandwidth? Your actual characteristics of the amplifier will be something like this. So what is your desired one? This is your desired, right? What you will check then? 3 dB below the desired point, and that is this point. Because when your pole 1 is hit, beyond that your gain drops drastically at a minus 20 dB per decade of slope. We may not even reach up to pole 2. The gain is so dropped that this will no longer be this can no longer be used as an amplifier. Okay, so that is why to calculate the bandwidth I will consider only this, because this is ultimately giving my 3 dB bandwidth. So whatever I am considering is P1, and obviously I know that my there is no zero in the system, or there is so there is no pole associated with the system at lower frequency. It is kind of a low pass response. So my bandwidth will be P1 minus 0 equal to P1. Okay. So if you calculate from this the value of P1 and then calculate the value of bandwidth, you will see that this is coming around 14 megahertz, and this will come around approximately around 300 megahertz. Okay, so you cannot use your amplifier below 40, beyond 14 megahertz, because you can see this is your desired gain. If you use at near pole 2, your desired gain is dropped by so much, it cannot be used. Okay, is that clear?
Yes.
Okay, so another characteristics we see generally in common source amplifier, which you must have seen in books as well, is something like this, right? Common source gain bandwidth plot. So we have seen the origin of this. This is nothing but your this. Why is it coming from? Is it coming? Why it is coming from? It is coming from your CGS and CGD. If your CGD can be ignored, then my Miller effect can be ignored. Then I do not have this another pole. You see, this second pole is completely dependent on CGD2. So basically, if you do not have CGD, you do not have this. Only you have one pole, and or you have minus 20 dB plus minus 20 dB per decade slope. That is what is basically considered in your textbooks. But why is this pole coming? This is coming from the coupling capacitances. basically if you draw your amplifiers, the way you apply your small signal is this, and let's say at this point you want to bring out your output voltage. So this C1 and C2 are causing your this pole. Okay. So in some of the questions you may have seen, or you may encounter that they will ask you about this is called mid-band gain. Okay. But be assured that this is they are talking nothing but the DC gain of the system. So this is only this part that we have analyzed. Okay. And also there is a common term called gain bandwidth. Gain bandwidth product is constant in common source amplifier. Be very wary of that. That is not always true. Okay. It depends on the circuit topology and how you make that. For not all common source amplifier, gain bandwidth product is constant, and it is not absolutely true for common drain and common gate structures. Yes, you are asking something.
Just saying that, can you repeat that part, what you said after midband gain, because your voice was break, I
Okay.
guess.
So what I mentioned that, so you have understood, right? This is mid-band gain is the same thing as your DC gain, what we have analyzed.
Yes, sir. Yes.
But without the because we have analyzed without the coupling capacitances, so we did not encounter this pole. Okay.
Okay. Okay.
So, and also another thing is I mentioned that in common source amplifiers, there is a statement that gain bandwidth product is always constant. So that is not always true. So be very aware of that statement, when to use it and when not to use it. If in question it is given, that is fine, but understand that very carefully. For not amplifiers, gain bandwidth product will be constant. First, even not for all common source structures, gain bandwidth product will be constant. Okay. So we'll continue next week.
Okay, sir. I have
Yeah.
one query.
Yes.
Sir, why we are using the DC gain when we are using capacitors in the circuit?
DC gain when you are using capacitor in the circuit, because you mean to say why we are using DC gain to do the Miller,
Yes. Yes.
this one, right?
Yes, sir. Yes.
Okay. So basically what you are doing, you are basically opening up the capacitance at the output and putting some two different capacitances, right? So your effective capacitance value is getting increased or decreased. So you can see your effective capacitances values are increased, right?
Yes, sir.
And what does that mean in the impedance term? 1 by j omega c. So you can consider low frequency as well to see the same impedance. Your z is equal to 1 by omega c, right?
Yes, sir. Yes.
So you are increasing your c, so you can consider your lower frequencies.
Yes, sir.
So that's why
Okay.
you can consider low frequency gains. Okay.
Okay, sir. Okay.
I think that's all. Thank you. Let's continue next week. Next week means this coming Monday. Okay. Day after tomorrow, we'll have a session 6 to 8.
Sir, I have one request.
Yeah.
Can we schedule that class from 7 instead of 6 in
Uh,
Monday?
Actually, what I have done, I have emailed the IIT Madras NPTEL team regarding that. So it will be very difficult to, reschedule that at this moment. But I'll try to cover most of the concept in the second half of the session. Okay, you don't worry about that. So we'll try to see how we'll do. You can join at 7, but we'll see. There will be mostly discussion based on amplifiers only. So the important discussions I'll start at 7 mostly, if that is what I can do.
Okay. Okay.
Okay. Okay. Thank you.